Okay, so let's just start from a very typical introduction of the CCUS and the importance of the carbon capture, utilization, and storage to address global warming. As you know, human activities have increased the concentration of the carbon dioxide in the atmosphere to be much higher than what has been determined as the safe level. That's why the carbon capture, utilization, and storage has been introduced to the world to capture CO2 and transport it and store it somewhere safe, such as the geological formations. To find the best place and the most appropriate CO2 storage sites, scientists and researchers got inspired from the nature in which natural gases were trapped in the geological reservoirs for a million years, which then were produced and transported to be used within the refineries to heat our buildings, houses, and for transportation in our daily life generally. That's why this conclusion has been made that the oil and gas infrastructure, such as depleted oil and gas reservoirs, and also transportation pipelines, which have the suitable capacities and capability, can be reused for the CCUS processes. However, there are some significant challenges and problems associated with this strategy. And in this webinar, I'm going to introduce you the potential problems and also potential solutions of the those problems in the CCUS and hydrogen economy systems in 4 different steps. First, I would like to describe how do CCUS and hydrogen systems look like, and how the CO2 and hydrogen-rich blends and streams are transported and stored in the geological formations, and what the challenges are in this way. Then I will describe the challenges which parts of the system might face the significant issues and barriers, such as flow measurement errors for both hydrogen and CO2, the corrosion and reservoir rock dissolution and precipitation problems. Then I'll go through the theory and thermodynamics behind it, and then try to tell you why these problems are happening within the field. And once we have that theoretical understanding, then we would try to engineer some solutions for it. Okay, as you might have heard about the energy transition strategies within the UK continental shelf to reach net zero target by 2050, and hopefully by 2045 in Scotland. We have different strategies in this regard, and one of the key strategies is reusing and repurposing the existing oil and gas infrastructure for the CCUS and hydrogen applications. However, there are some significant problems against this kind of strategy, as I mentioned in the last slide. And the first one, and one of the most important one, is the errors in the performance of flow meters and the errors in the CO2 or hydrogen flow measurement. As you know, it's very important to measure CO2 and understand that how much CO2 we capture from power plants, or let's say blue hydrogen production units, potentially in the future, and know that how much CO2 we are going to store into the geological formation. So that's why flow measurement is key for us. CO2 flow measurement is very important for us. But the presence of impurities within the CO2 rich blends would cause significant errors in performance of the flow meters. Then we might have the problematic two-phase liquid gas flow within the transportation network, and also those harmful impurities and some polar components like water after condensation of the water in the transportation network. We might face the corrosion problem, asset integrity, and sweet scaling, and also potentially CO2 reservoir rock dissolution and precipitation and associated leakage challenge due to the lack of compatibility of the CO2 rich blends with the host reservoir rock materials. And also the corrosion problem, as you know, is the lack of the compatibility of the CO2 rich balance and presence of some harmful impurities with the pipeline materials. But the good news is that all these problems and challenges are somehow related to the thermodynamics and fluid properties of the CO2 rich stream. So if we would have access to reliable experimental data sets or the model predictions of the phase behavior of the CO2 rich systems, or the key thermophysical properties of the CO2 rich balance, then we would somehow overcome all these challenges, hopefully. And let's keep fingers crossed for that, of course. Okay, so let's dig into the first problem, errors in the performance of the flow meters and in the measurement of the CO2. The key question is that how can we reduce the actually the errors in the CCS flow measurement and the flow metering of the CO2 rich blends. In order to answer that question, firstly, we need to realize the importance of the thermodynamics and thermophysical properties of the CO2 rich blends. Here you can see the actually the metering locations along the whole CCUS value chain, at which the very accurate flow measurement of CO2 is required for us for the purpose of the custody transfer, and also the regulatory metering described by EU or UK legislation on the CCUS. And also you can see the stream composition and also the range of pressure and temperature. For example, for the temperature ranges from 20 to 80 degrees C, which are presumably to be encountered at the metering points along the whole CCUS value chain. And all this information, I mean the pressure, temperature, and composition, would be fed into the thermodynamic models and equations of a state for accurate determination of the phase envelope, phase behavior of the CO2 rich blends, and also the determine the thermophysical properties of interest, whatever needed for the CO2 rich blends. As you know, we have different metering technologies for CO2 applications. One of them is ultrasonic flow meter, and the recent one and the hot topic on the flow measurement is application of the Coriolis meter for the CCUS and CO2 rich blends. And for these two flow meters, determination of the key thermophysical properties such as density for Coriolis meter, as the secondary measurement of Coriolis meter is density, and speed of sound for ultrasonic flow meter, as this secondary measurement of the ultrasonic flow meter is the speed of sound, would be needed for flow meter verification and flow meter diagnostics. So that's why it's very important to determine those properties for flow measurement aspect. And also the phase behavior are also very important for us to know that the flow meters would perform perfectly if we would operate within the single phase flow. And also in terms of the flow assurance aspect, it's very important to know that what is the phase behavior of the CO2, whether we have the water condensation, determination of the dew point through the experimental data sets, and using some equipment, and also using thermodynamic models, are all very important for us to address the flow measurement and flow assurance challenges in the CCUS value chain. Okay. Okay, so in this slide, you can see the actually experimental data, some experimental data, limited experimental data, and modeling results for the density values of the CO2 rich blends in presence of key impurities, the main impurities such as methane, nitrogen, hydrogen, and carbon monoxide, for different pressures and at a constant typical temperature of 40 degrees C. And we have used 5 different equations of states such as SRK, Payne-Robinson, Valderrama-Patel-Teja, PC-SAF, and Gerg equation of state for our thermodynamic modeling of the studied CO2 rich balance. And as you can see, with increasing the pressure, we have increased in the densities of the CO2 rich balance. And compared to the pure CO2 system, the presence of impurities reduces the density of the system. And actually we can see that the all models and the equations of a state could successfully predict all the trend of densities for different CO2 rich streams studied in this project. In this slide, you can see some experimental data and modeling results for the speed of sound for CO2-rich binary blends in presence of 4 mole % of nitrogen, hydrogen, methane, and carbon monoxide, again for different pressures and the constant temperature of 40 degrees C, at the same condition actually for the density in the last slide. And again, we have used 5 equations of state of SRK, Payne-Robinson, VPT, PCSAF, and GERC to model that. And as can be observed within the results, with increasing the pressure, we have increase in the speed of sound of CO2 rich streams. And compared to the pure CO2 system, the presence of methane and carbon monoxide actually reduce the speed of sound of the system due to the larger size of these molecules compared to the CO2 molecule. And on the other hand, because of the smaller size of nitrogen and hydrogen molecules compared to the CO2, the speed of sound for those two systems are higher compared to the pure CO2 system. And again, you can clearly see that again all the thermodynamic models could successfully predict the trend, and also the speed of sound values for the studied CO2 rich systems. Okay, now the question is that how we can make sure about the accuracy and reliability of the model predictions. So in order to do that, here you can see the thermodynamic model validation through comparing the modeling results with the experimental data. And here we presented the average deviation of the modeling results from the experimental data for both density and the speed of sound to assess and evaluate the outcomes of different utilized equations of a state, from the classical cubic equations of a state to the new ones and relatively more accurate ones, let's say, Gerg equation of a state and PCSAF. And as can be seen, the Gerg equation of a state has the lowest deviation compared to the other models, and it is the most accurate and reliable model for determination of the thermophysical properties of the CO2 rich systems, at least for the studied systems in this project. Okay, now in this slide, you can see the the transition, the phase transition from a two-phase blend to supercritical fluid. In the top left picture, liquid and gas exist in equilibrium, and a liquid vapor roundel is well recognized at this point. However, it becomes less recognized as the blend makes the transition to a single supercritical fluid. And as the temperature is increased, the difference between the gas and the liquid density is reduced, as can be seen in the bottom right picture. And now you can see the phase envelope and the VLE graphs of the CO2 rich streams in presence of nitrogen, methane, carbon monoxide, and hydrogen impurities, using Gerg equation of a state as the best model among the others. And as can be seen, all these impurities open up very challenging two-phase liquid gas region, and in presence of the higher concentration of impurities, the phase boundaries would be shifted to the left side, and actually the presence of very low concentration of impurities again would open up these two-phase liquid gas regions, and it would cover wider range of temperatures, and it's really problematic and challenging when we are operating in the offshore environment or subsea environments, when we have significant change in the temperature along the whole pipeline. And to conclude that, if we want to have lower uncertainties in the determination of the CO2 flow rate and flow measurement of CO2, we need to operate within the single phase. We need to recognize and accurately determine the phase envelope of the CO2 rich blends, and then try to operate within the single phase to avoid those problematic conditions. Two phase, I mean, conditions which would lead to errors in performance of flow meters. And if we would operate within the single phase, and if we would have that possibilities, then that would be great for us. Okay, so let's talk about the second and third problems of the CCUS systems if we would reuse and repurpose the existing oil and gas infrastructure. And as you know, there is always big concern for governments and the energy operators worldwide about the risk of the CO2 leakage from transportation pipelines or subsurface reservoirs. And if that happens, all the efforts we have made for capturing, transporting, and storing CO2 would be wasted. And the significant question for us would be that how we can avoid those problems and potentially the leakage challenges associated with the CO2 rich streams. And in order to answer that question, firstly, we need to know that what is the main driver for the corrosion, reservoir rock dissolution, and precipitation after injecting CO2 into the depleted oil and gas reservoirs, or even for the case of the deep saline aquifers. So the pH would play a critical role in this regard. So here you can see the anode and cathode reactions participating in the electrochemical corrosions. And when we have even the trace amount of water, hydrogen sulfide, or generally the polar components as impurity in the CO2 stream, the carbonic acid will be produced, and this acidic solution is more reactive compared to the pure stream without any problematic impurities, and can attack to the pipelines. And due to the formation of the carbonic acid, more ions like proton and bicarbonate will be released into the aqueous phase, into the solution, which increments the conductivity of the solution, and therefore the pipelines will be prone to the higher degree of corrosion. And in case of the geological porous media, like as I said, depleted oil and gas reservoirs, or the deep saline aquifers, when the CO2 with impurities would be injected into the reservoir down there, then it would be mixed with the brine or the formation water, and the carbonic acid would be produced again, which it speeds up the rock dissolution and precipitation problem. And as a result, CO2 could penetrate into the upper layers, which increments the risk of the CO2 leakage, or in other words, the safety and security of the reservoir and the whole CO2 storage process would be reduced significantly. So here in this slide, you can see some experimental and the thermodynamic data, modeling data for the effect of the pH changes and the effect of the salinity of the aqueous phase on the pH changes for actually different CO2 aqueous phase systems, brine systems, in presence of variety of salinities in the aqueous phase and different ionic strength. And as can be seen, when we increase the salinity of the aqueous phase, the ion activity coefficient of the proton will be increased after injecting CO2 into the water, and then the pH of the system would be decreased accordingly, which means that we have more acidic environment, and the risk of reservoir rock dissolution and precipitation, or the associated corrosion problem would be increased as well. And the good news is that the model could successfully estimate all the behaviors of the pH variation of the brine or the aqueous phase after injecting CO2 into the system. And we can safely say that our model can tell us that deep aquifers with lower salinity and lower ionic strength are much better candidates as the geological storage sites for the CO2 geological storage purposes compared to the higher salinity reservoirs with the higher ionic strength due to the lower degree of the rock dissolution precipitation, which caused the potentially the formation damage problem in that case. Okay, so in order to actually validate our claim, we have used the visual observation of the effect of salinity and pH changes on the reservoir rock dissolution using macro CT scanner and 3D images and video. As you can see, that these images and videos can be taken from have been taken from the rock sample before and after the experiments, and you can see that based on the results and these macro CT imaging in this video, you can see the red color which highlighted the dissolved grains. So these regions are demonstrated as the pore spaces in the image on the right, and these 3D video and images enable us to calculate the volume of the dissolved grains. And based on the results, the pore space for the rock sample, which was exposed to the higher salinity and the higher ionic strength, AQS phase was increased by 18%, while the rock phase reduced by 4%, and the rock sample in contact with the lower salinity brine, the increment in the pore space was measured 9%, and we had the reduction in the rock phase by 2%. And by comparing these results, we can safely conclude that the high salinity brine has induced more reservoir rock dissolution and potentially the precipitation of that, as discussed in the last slide, and also described by our thermodynamic model. Okay, very good. So, ladies and gentlemen, I have very good news for you that we are in the middle of this webinar. So, within the next hopefully 15 minutes or so, the webinar will be finished, and then you can enjoy the rest of your day. So, but now I would like to talk about the hydrogen system, hydrogen economy systems, and the importance of thermodynamic for the hydrogen. Just a second for the water break. Okay, sorry about that. Okay, so talking about the hydrogen systems is very important, key in the UK potentially, and also worldwide. Is a hot topic, and it's very important for us to know that why we need hydrogen, why the hydrogen flow measurement is very important for us, and also we need to know that why the thermophysical properties and thermodynamics of hydrogen streams for different processes are very important and significant for us. From the actually hydrogen production, either green or blue or whatever color it has, to its transportation and storage into the geological formations. In order to determine the properties of the hydrogen containing blends, firstly, we need to know that what the composition of the stream is, like the CCUS case, as I mentioned, and also it's very important to know what the temperature and pressure operating conditions are, as we use all these data as the inputs of the thermodynamic models. And also, depending on the composition of the stream, then we can, and also the PT condition, we can design our experiments if we want to do some experimental measurements for the thermophysical properties of interest. And at the end, we will see that how this predicted fluid properties and thermophysical properties of hydrogen could be employed for the optimizing and designing a secure hydrogen transportation and geological storage processes, and also accurately measuring the amount of hydrogen or hydrogen flow rates to be sure that we are getting that much hydrogen we paid for at the hydrogen refueling stations, or for the building process for our buildings and our homes in the near future in the UK, and also hopefully worldwide. Okay, so firstly, I talk about the importance of the hydrogen and talk about the blue hydrogen and the importance of its properties. And we need to answer this significant question that why do we need to study about the hydrogen streams and their properties? As all of you know that in order to reach net zero target by 2050, hopefully, we need to reduce the amount of carbon emissions from fossil fuels, and the energy transition strategies to employ the carbon energies should be undertaken in the near future. So the hydrogen has great potential to help us with decarbonization of our environment in different sectors, including the transportation, heat and power, and that's why we need to know and understand about the properties of hydrogen containing systems. And also it's very important to know that what the operating conditions of these streams are. So as you know, we have different colors for hydrogen: green, blue, gray, etc. So we for the blue one, which is could be very interesting in the UK in terms of both at the same time producing hydrogen and also maximizing economic recovery for producing more gas from offshore assets in the North Sea, then blue hydrogen could play a critical role. And for each kilogram of hydrogen, we would produce 7 kilograms of CO2 from that blue hydrogen production unit. So that's why we need a CCUS process, which should be integrated into the blue hydrogen production unit, and it should be optimized to capture that CO2 and then transport it and store it into the geological formations, potentially in the offshore assets in the UKCS, and also generally the potentially depleted gas reservoirs in different countries. So as I said, the PT operating conditions are key for us to realize that which ones are very important, and for each thermodynamic modeling and also the experimental as well. In addition to knowing that what the compositions are, we also require to know and understand the operating conditions of interest for hydrogen-based systems. While the thermodynamic properties of the pure hydrogen are very well established in the literature, but the published data for the hydrogen gas mixtures in the literature, particularly related to the geological formations and even the transportation network, have not been very well covered in the literature in the full range of, for example, covering different gases and also different PT operating conditions of interest that we would face in industrial scale. So, but here in this slide, you can see the pressure and temperature ranges for different hydrogen-based economy systems, including the vehicle storage tanks, surface storage tanks, the transportation pipelines, and hydrogen production technologies, actually. And also, it's very important for us to know that which thermophysical properties of interest are important for different processes along the whole hydrogen economy system and the value chain. So here you can see the potential applications of thermodynamic properties of hydrogen containing systems for geological hydrogen storage, flow metering, gas separation, other types of hydrogen storage such as gas hydros or metal organic framework, and the thermodynamic data like the phase diagrams, viscosity, density, values of the hydrogen containing systems can enable the researchers and scientists worldwide to have a deeper understanding of the potential reactive fluid flow through the purse media and also transportation infrastructure for the hydrogen transportation and also geological storage purposes. And also they can be used for accurate flow measurement of the hydrogen streams. And in general, the thermophysical properties of hydrogen containing gas mixtures over a wide range of pressures and temperatures can be used for designing and optimizing the hydrogen production units, as well as the transportation and storage processes for the hydrogen-based economy systems. Okay, so now in this slide you can see actually the theory and the thermodynamic model behind all the calculations that I will present within the next slides. In this study, the very regarded Gerg equation of a state has been integrated with supertrap model to estimate the phase behavior, viscosity, and density of the gas mixtures relevant to the hydrogen transportation and storage, covering the thermophysical properties of the gas phase, liquid phase, and supercritical regions. In the Gerg equation of a state, we have used dimensionless Helmholtz energy, which is function of inverse reduced temperature, reduced density, and molar composition of the gas blend, and consists of two parts. The first part is for the ideal gas contribution, as you can see here, and also it's the function of the number of mixture components and the mole fraction of each component in the system. And the second part is the residual part of Helmholtz energy, which is function of dimensionless Helmholtz energy of each component in the ideal gas phase, and the departure function, which is again function of density, temperature, and also composition. For determination of the viscosity of the system, we have used a supertrap model that is composed of the dilute gas and residual contribution part, and is function of the temperature and density. Okay, here in this slide you can see the estimated value coming from the thermodynamic modeling for different hydrogen blends with methane, carbon dioxide, and a typical North Sea natural gas for mole fraction of 90% for hydrogen over a wide range of pressures and temperatures using a Gerg equation of a state. You can see also the composition of the natural gas, typical North Sea natural gas in this study in the blue table here. And as you can see, the density values of the mixtures are greater in presence of the CO2 compared to the methane and natural gas in the study systems, as the density of CO2 is higher than of methane and natural gas, and for natural gas is higher than methane. And the densities of the stream increase with increasing pressure for all isotherms and at constant temperature, and reduce with increasing temperature, as you can see in the graphs in this slide. And also you see in this slide, you can see the density values again for variety of hydrogen streams with carbon dioxide, methane, and North Sea natural gas for mole fraction of 50% for hydrogen at various temperature and pressure conditions. And in comparison to the results from the last slide, we can see that the density values of the blends in presence of higher concentration of hydrogen are smaller compared to the lower concentration systems for hydrogen. And again, here we can see the same trend of density changes with temperature and pressures. And the densities of the mixtures increase with increasing pressure and for all isotherms, for all temperatures, and decrease with increasing the temperature. Okay, in this slide you can see the modeled viscosity values for different hydrogen blends, again in presence of the CO2, methane, and natural gas for hydrogen mole fraction of 10% at different pressures and temperatures using integrated Gerg and supertrap model. And the viscosities of the mixtures increase with increasing the pressure and temperature, and this can be attributed to the fact that an increment in pressure and temperature increases the velocities of the random motion of the molecules, the gas molecules, and as such, collisions of the gas molecules would be increased in the system, which resists the flow of the gas and accordingly increases the viscosity within the system. And the unusual behavior of the methane or carbon dioxide rich blends at lower temperatures, as you can see, is because of their proximity to the methane or carbon dioxide critical points. And in this slide, you can see again the viscosity values from the thermodynamic model for different hydrogen blends in presence of methane, CO2, and natural gas for mole fraction of 50% for hydrogen at various pressures and temperatures, again using integrated Gerg and supertrap model. And compared with the results in the last slide, we can safely say that the viscosities of the mixtures are suppressed with increasing the hydrogen mole fraction in the system, as the hydrogen has significantly lower viscosity compared to the methane, carbon dioxide, and natural gas due to its smaller molecule size. Okay, so it's very important for us, particularly for the people who are interested in the blue hydrogen production and also its transportation and storage. As you know, the blue hydrogen production is coming from the methane reforming process, which is an endothermic process and needs a huge amount of heat to be conducted and to be completed. So when we inject hydrogen into depleted gas reservoirs, on the other hand, for the hydrogen geological storage purposes, it would be mixed with the methane and potentially have a reactive fluid flow through porous media due to the chemical interactions with the rock surface with the host reservoir rock materials due to the high pressure and temperature conditions in that environment. So it's very important and crucial for us to understand the thermal conductivity and thermal capacity of the hydrogen and methane mixtures, generally for any blue hydrogen production and storage and also transportation project. And in this slide, I'm going to present you these properties for the hydrogen methane blends. Here you can see the estimated isobaric heat capacities for variety of hydrogen and methane blends for different hydrogen mole fractions over a wide range of pressures and temperatures. And you can see that the thermal capacities have higher values for higher hydrogen mole fractions, as the heat capacity of pure hydrogen is greatly higher than of the pure methane at temperatures and pressures above the critical point of methane. And it can be observed that with increasing the pressure, the thermal capacities would be increased for all isotherms and temperature conditions due to the increased intermolecular forces within the hydrogen methane system. And here in this slide, you can see the results of the modeled values for the thermal conductivity, again, for a variety of hydrogen methane blends with a range of hydrogen mole fractions over under different conditions of pressure and temperature, again using integrated Gerg as supertrap model. And it can be seen that for all hydrogen methane blends, the thermal conductivity values increase with increasing pressure for all isotherms, and the thermal conductivities would also increase with temperature for high hydrogen mole fraction systems above 50%, as you can see here in the graphs here in this slide. And these behaviors can be attributed to the fact that increasing the pressure or temperature increments the molecular motion, which results in improving the condition of heat within the gas molecule, and also the heat transfer between the gas molecules within the hydrogen methane system. And the unusual behavior of the methane rich blends here at lower concentration is because of the proximity of those points to the methane critical point actually. And the thermal conductivity values, you can safely say that the it would be increased with increasing the hydrogen mole fractions, as pure hydrogen has much higher thermal conductivity compared to the methane molecule. Okay, in this slide you can see the phase diagrams and the VLE graphs of different hydrogen blends, hydrogen, methane, natural gas, and carbon dioxide blends. So these envelopes have been calculated for the for these systems of interest using the Gerg equation of a state. And as you can see, some parts of the two-phase liquid gas region of the hydrogen and carbon dioxide and hydrogen and natural gas systems happen within the pressure and temperature ranges of the geological storage sites, and also the transportation pipelines for transporting hydrogen, and also and that's why it's very important for us to determine the phase envelope of the hydrogen containing systems in presence of such components in the system, like carbon dioxide or the hydrogen natural gas blends for UK's national gas transmission and distribution network, when we would introduce hydrogen into the system, or if we would have CO2 in the system for the case of blue hydrogen. And now again, similar to the CCUS modeling, again, the question is that how can we make sure about the accuracy and the reliability of the model predictions using the Gerg equation of a state for the hydrogen containing system studied in this project and presented in this webinar. So we have tried to evaluate this. Generally, the determination of the accuracy of Gerg equation of a state for different binary mixtures is very challenging, and as there is a gap in the literature regarding the experimental available for the different ranges in terms of the composition of the stream, and also regarding the pressure and temperature operating conditions. So that's why the absolute value of the error for such ranges studied here is very difficult and challenging. But here we have just used some published density data of hydrogen and methane mixtures in the literature at the range of pressure and temperature conditions to just analyze and assess and evaluate the reliability and accuracy of the modeling data from Gerg equation of a state. And as you can see, we have presented the relative deviations of the predicted densities coming from Gerg from the experimental data for the hydrogen methane blend, and we have calculated the average absolute deviations, AADs, for the Gerg equation of a state modeling data from the experimental data for a variety of pressures and temperatures. That is 0.044 for the hydrogen mole fraction of 10% in the mixture, I mean the hydrogen methane mixture, and 0.006 for the hydrogen methane blend with the hydrogen mole fraction of 50%. So the very low AAD values here, you can see that it can confirm the high accuracy and reliability of the Gerg equation of state predictions with very relatively low errors, and you see here in this slide, at least for the results on the density. Okay, so in this slide, I'd like to present you the recent advancements in the building of our facility, and quite unique experimental facility at NEL for determination of and measurement of thermophysical properties of CO2 and hydrogen-rich blends. This project is funded by UK government as part of Flow program project funded by DSET, Department for Science, Innovation and Technology in the UK. And in this test rig, we can measure simultaneously speed of sound and density of both hydrogen and CCUS streams in the wide range of impurities in presence of different impurities, such as, for example, for the case of CO2, such as hydrogen, nitrogen, methane, argon, oxygen, or even water at ppm level, NOx and SOx, and at different phases from gas phase to the supercritical region, including the dense liquid, obviously. And the operating condition is from 1 to 400 bar, and also the temperature range is from -20 to up to 150 degrees C. So, and it's very important because for us to have this facility operational at NEL, to fill the gaps in industry and also in the literature, to generate some data to cover the specific compositions for both CCUS and hydrogen rich blends, and also cover wider range of PT operating conditions. And it's very important time for us to have wonderful projects with this facility. And within the next couple of months, we will have a PhD student who will work on this facility at NEL to generate some experimental data sets. So, and hopefully more projects will come in the near future for generating the thermodynamic data sets. Okay, so the last slide about the wrap up and conclusion of this webinar. So we are at the end of the webinar, and just wanted to conclude that. What are the problems? What are the solutions and significance of the potential solutions to address the challenges regarding the CCUS and hydrogen economy systems? We are going to talk about all of these in this slide. So if you want to just repurpose oil and gas infrastructure for CCUS and also hydrogen applications, we would face some barriers and problems related to errors in performance of the flow meters, as well as the high risk of corrosion, asset integrity, and the rock dissolution problem, which lead to the CO2 leakage. We saw that all these challenges are somehow related to the fluid properties and thermodynamics of CCUS systems, and also the hydrogen containing streams. So firstly, we need to understand the theory and thermodynamics behind the whole CCUS and the hydrogen value chains. And in this regard, we require to develop appropriate thermodynamic models to predict the properties of CO2 and hydrogen rich blends, such as density, speed of sound, phase boundaries, and even pH for application for the corrosion and the reservoir rock dissolution. And at the end of the day, if we would have such accurate thermophysical properties of CCUS and hydrogen systems, then at the end of the day, we would have more accurate flow measurement system, safer and more secure CO2 and hydrogen transportation and geological storage processes, through avoiding the problematic conditions, operating conditions, which lead to those challenges and barriers such as corrosion, rock dissolution, and the high errors and inaccuracy in the flow measurement of hydrogen and CO2. So hopefully it's very important for all of us in the community, in industry, to address all these technical and some scientific challenges in the CCUS and hydrogen sectors. And hopefully one day all of us would overcome these challenges and we would reach net zero by 2050. Thank you so much, and hopefully you enjoy this webinar. Yeah, thank you.
Thanks, Edris. That was good. Certainly sparked a lot of interest. We've got a lot of questions posted. So before I dip into those, you'll see on your screen some related training courses that we're running. As you've attended this webinar, you are entitled to a discount. So if you're booking any of these training courses online, if you type in webinar 10, and you'll get a discount off the normal price of those training courses. Okay, Edris, we've got a lot of questions, so we'll just jump straight into them. First one I've got here. What are the accuracy requirements for flow metering in the CCUS systems? So I suppose by accuracy we're talking uncertainties, aren't we, Edris?
Yes, exactly. So So as far as I know, so this is the topic that at the moment we are doing research on, and also we are developing facilities for the CO2 flow measurement, particularly for the dense liquid phase. We have some capabilities for the gaseous phase, but we are developing the standards and also the infrastructure for measurements of CO2 in the dense liquid phase. And as far as we know, I think that if I remember correctly, it would be something around 1.5%, but it's under debate. Someone say that it would be, for example, something around 2 or 2.5% would be achievable, and someone say 1.5%. But so the problem is that we need a laboratory to do the measurement and confirm all these uncertainties for the industry. And we are quite active in this regard through development of such facilities at NEL in the near future. Yeah.
Yeah. So I guess once the research is done, then a standard will then be applied, and that kind of the uncertainties will then be defined. Then, yeah.
Yeah, exactly. And but the lowest uncertainty that I saw is in the reports is the 1.5%, but it's under debate that it's achievable or not. So this is the lowest one,
Yeah.
1.5%, and
Okay.
the highest one was 2.5%. But yeah, as I said, it needs the experimental measurements, of course, and also applying different types of metering technologies in the lab at different conditions.
Yeah. Okay. What are the top three parameters or quantities to monitor for in CCUS systems?
So in terms of thermodynamic properties, I can safely say that for flow measurements, it's density, viscosity, and also the phase behavior of CO2 are very important and key parameters to know that whether we would face any errors in performance of flow meters or not. In terms of flow assurance, again, phase behavior plays crucial role, whether we would have single phase gas or liquid or multi-phase fluid flow, or even we would have formation of the solid like clathrate hydrates at a high pressure, low temperature environment. So again, phase behavior is very important. So and also depending on the type of metering technology, like for example ultrasonic flow meter, the properties such as speed of sound would be important for us as well. But yeah, the generally speaking, phase envelope, the VLE phase diagrams of the CCUS systems, density and viscosity are very important. And then after that, speed of sound for ultrasonic flow meters, and also understanding of thermal conductivity would be important for storage purposes as well. Yeah, and also solubility of CO2 in the host reservoir fluid for the storage purposes. Yeah.
Okay. This next one, very kindly refer to slide 14. How is it proposed to manage brine salinity pH over storage reservoir lifetime? So this refers to your slide 14.
Yeah.
Yep.
So so for doing that, so I think firstly we need to understand the composition of the host reservoir fluid first. If it would be deep saline aquifers, so the ionic strength, the type of ions in the aqueous phase are very important for us and key to do initial assessment of whether this geological storage site or this deep saline aquifer would be the best and the most appropriate storage site for us for as a long-term plan, depending on the solubility and dissolution of the CO2 rich system into the aqueous phase based on the ion types and the ionic strength of the aqueous phase. So that's why for selecting the most appropriate geological storage site for long-term CO2 geological storage, or let's say permanent storage of CO2, then understanding of these parameters are very important, and we need to do initial assessment not only on the pH, and dissolution of CO2 into the aqueous fluid, but also the compatibility of that fluid, resultant fluid, with the host reservoir rock material, and to understand the geochemistry behind it, and see that how the rock would be dissolved in contact with the reactive fluid.
Okay. Right. Have you checked the viscosity model predictions of H2-rich mixtures with supertrap model versus experimental data or field measurements?
For the in this actually in this project, we just compare the results, the modeling results for to the experimental data for density, not specifically for viscosity. We didn't have access to that on that time, but we have planned to generate the some viscosity data sets, experimental data sets, I mean viscosity measurements for different hydrogen containing blends in presence of methane and also natural gas for regarding the UK's transmission distribution network, to target that in the near future, and then compare the viscosity data set, experimental data set, with the modeling outputs. So this is our plan to do in the near future.
Okay.